Hello everyone. Now, dear students, in second lecture we have studied about the translation vector and the primitive unit cell. Now in this lecture we are going to see about the symmetry operations. Students, the first is that what do you mean by the symmetry? Now when the two or more parts are identical after the flip, slide or the turn, now then we can say that there is the symmetry. In this universe we can see the number of examples of the symmetric operations. Now taken one of the example is the butterfly. Now in this picture of the butterfly we can see that these two wings of the butterfly are very identical. When the butterfly closes these two wings, when they overlap with each other, that times we can say that they are very coincide with each other. Now in case of that, another example, now we can see that there is the symmetry in the every leaf of the every tree. This is one of the leaf of the tree, and we can say that if we bisect it into the two parts and if we overlap it one over the other, now then that overlapping will also very coincide. Now in this third example, in this third picture, now these are the number of the leaves of the one of the plant, and in every leaf we can say that there is the symmetry. Similarly, we can observe the symmetry in the every fruit also. This is one of that the fruit. If we divide it into the two parts, now then we can see that there is also the symmetry. Therefore, the images which can be divided into the identical parts, then such images are the symmetrical images. Now similar to that, all these examples, now we can see there is also the symmetry in the crystalline structure. Now in second lecture we have studied about how the crystalline structure get formed with the help of the lattice and the basis. And then once the structure get formed, now then we can observe there is the symmetry if we use the symmetric operation inside that the crystalline structure. Now taken the examples related with the physics. Now take one of that, the example of equilateral triangle. Suppose if we consider the ABC is one of the equilateral triangle. Now this is the centroid through which the axis of the rotation is passed. Now at the every vertex there is the atom is situated. Now if we rotate this vertex through the 120 degree. Now after the first rotation, now then the vertex B takes the position of the vertex C, and after the next 120 degree rotation, the vertex B again takes the position of the vertex A. Again if we rotate it through the 120 degree, then the vertex B come to its original position. So through this 360 degree rotation, we observe here there is no change in its structure. So the structure of the equilateral triangles remains as it is unaltered. Now take an example, such a type of, that means here through the rotational operation we can see here there is no change in its structure. Similarly, take another example. Take one of that, the triangle ABC. If we held the thin mirror perpendicular to the plane of this triangle along the altitude B, now then we can see the reflected image of the triangle, half of that the triangle inside that the mirror, and both images are very equal. So here we can see that there is also no change in its structure if we use the symmetric operation there, and that is the reflection type of that the symmetry. Therefore, such a type of that the operation, when we operate it inside the crystalline structure, now then that is known as the symmetric type of the operation. Therefore, we can say that there exist certain operations when operated on a given structure, the structure remains unchanged or invariant, and such a operation is called the symmetric operation, and the structure is said to possess the symmetry under that operation. Now we are going to see the different types of the symmetric operations when we use such a type of that the operation in a crystalline structure. Basically, there are the two types of the symmetric operations. One is known as the point group symmetry, and second one is known as the space group symmetry. In a point group symmetry, the symmetric operations carried about a point or a line. That means when we do the symmetric operation, and that will be carried along at a particular point or at a particular line. Now then such a type of that the operations are known as the point group type of the symmetric operations. But when the point group symmetric operations are combined with the translation as well as the rotations, now then such a type of that the symmetries are known as the space group type of that the symmetry. Again, the point group type of the symmetries are classified according to the symmetric operation. The first one is the translation type of the symmetry, second one is that the rotational type of that the symmetry, third one is that the reflection symmetry under the mirror, fourth one is that the inversion through a point or the center of that the symmetry. Similarly, in case of that the space group type of that the symmetry, it is a combined symmetric operation, and we can observe such a type of that the combined symmetric operation in a screw type of that the symmetry, and second one is in a glide type of that the symmetry. Now dear students, now we are going to see in details about the point group type of that the symmetries and its different types of that the operation. Now the first one is the translation type of that the symmetry. Dear students, in second lecture we have already seen about the translation type of that the operation. That means when the atoms or the any lattice point, when it get translated from one lattice point to the another lattice point, or the unit cell when it get translated from the one unit cell to the another unit cell within that lattice structure, then there will be no change in its structure. So then such a type of that the symmetry is known as the translation type of that the symmetry. So we have already seen the different examples about the translation type of that the symmetry. We can translate the lattice point or the atoms or that the unit cell with the help of that the translation vector. That is, the translation symmetry is when something has undergoes a movement, a shift or a slide in a specified direction through a specified distance without any rotation or that the reflection. That means there is only the translation along the any specific direction through some distance, and that is known as the translation type of that the symmetric operation. Now we can translate the entire crystal structure by the translation operation, and with the help of the translation vectors and the translation vector operation. Now in this figure, now this is the two-dimensional square lattice array. Now here if we consider the 2 points, say as the vector A and the B corresponding to the two lattice points of this two-dimensional lattice structure. To understand or to operate the translation operation, we have to be consider one of the arbitrary point, say as the O at the lattice point, and that is the origin. Now if we connect the point A with respect to the origin, now then we get the position vector OA, it get represented by the vector R, and when we connect the point B to the with respect to the origin B O, now then the position vector OB is get represented by vector R dash. Then as we go from point A to the B, now then that translation is denoted by the translation vector, and that is the vector T. Therefore, as we go from A to the B or from vector A to the vector A dash, now then the vector A dash is given by using the law of the vector triangle, that is R dash is equal to the vector R plus vector T. In general, the translations, the relation of the translations vector can be expressed as vector T is equal to the n1A plus n2B. Now here the n1 and n2 are the integers, and the vectors A and B are known as the fundamental translations vector. Now in this way, in the lattice structure, we can translate the any lattice point or the any unit cell through some distance with the help of the translation, fundamental translations vector, and that is known as the translation type of that the symmetry. Now second one is the rotational type of that the symmetry. Similarly here if we consider the equilateral triangle ABC, now if it gets rotated through the 360 degree, now then it get coincide with the initial one. Now we have already seen once it get rotated through that the 360 degree centigrade, so there is no change in its structure, and such a type of the symmetry is known as the rotational type of that the symmetry. Now in this case here, therefore if that triangle, it can be rotated through the 120 degree also, through the 140 degree also, and 360 degree. Then it coincide with the initial one. Means if it get rotated through the 120 degree, now then there is no change in its structure. If that triangle get rotated through the 240 degree, even though there is no change in its structure. But below than 120 degree rotation, is there any change? Yes. That means the minimum angle of the rotation through which the structure remains unchanged, and that is the 120 degree. So now in case of this equilateral triangle, that means 120, so in this figure it shows that the structure will be the remains unchanged here. By using this minimum angle of the rotation, when the structure remains unchanged, then that times we can find the total number of the fold in the symmetry. Then how we can find that the total number of the fold? Now this is one of the equilateral triangle. Okay. Now if we fold like this here, so now this is the one fold. The another way we can fold like this here. This is the here this is the one. Now this is the second fold, and now here this is the three fold. That means along the three directions corresponding to the three vertex, we observe the threefold axis. Therefore, in case of that, every geometrical structure, we can find the number of folds also. Therefore, the number of folds is equal to be the twice pi divided by the minimum angle of the rotation which leaves the structures unchanged. So here, for finding the fold number, you should know that the minimum angle of the rotation in which the structure remains unchanged, and that is the very important. Okay, now in case of that the triangle, now we observe that the minimum angle in case of that the equilateral triangle, now the minimum angle of the rotation is the 120 degree. If we substitute this value, if we substitute the value of that the theta, now then you will get here that the total number of folds are the 3. Therefore here we can observe here, so this having the threefold axis symmetry. In case of that the cube, when the cube is rotated through about the vertical axis through the 360 degree centigrade, then there are the 4 positions of the cube which are coincide with the original position. Now see here, this is the cube here. So we can rotate this cube through the 360 degree centigrade. Now then we observe that the 4 positions, and at these 4 positions there is the different type of the fold axis symmetry. Now the first one is that, now like this here, if we rotate it, now the first one is that if the cube is rotated through the 360 degree centigrade, sorry, through the 360 degree. Now then what will happen here, if it get rotated through the 360, now then the structure will be remains unchanged, and then if we substitute the value of the 360 degree, now then there is only the one fold. So in any way here we can fold like this here, means there is only one fold. Now in case of that the second, if the cube is rotated through the 90 degree, when the position is completely identical with the original one, that means here like this here, if it get rotated through the 90 degree like this here, from this point to this point like this here, means what will happen here, through the only that if the angle of the rotation is the 90 degree, now then if we substitute this value of the 90 degree, now then we get here the fold axis type of that the symmetry. Now in case of that here, if the cube is rotated about the solid diagonal and if is rotated through the 120 degree, now then we get the threefold axis of the symmetry. That means here if we rotate it, this is the diagonal here from this point, this corner to this corner, and if we rotate it along the diagonal, okay, through the 120 degree, now then we get the threefold axis type of that the symmetry. Now in fourth one is that if the axis of the rotation is passing through the middle pair of the opposite, so this is the middle pair. That means here at this point and at this point here. Okay, if we rotate it through the 120 degree like this here, if we substitute the value of this is the minimum angle 180 degree, and if we substitute here in this formula, so we get here the twofold axis of that symmetry. So remember about that. What do you mean by the rotational type of that the symmetry? Now the next one is that the symmetry under the mirror reflection. A structure is said to have the reflection symmetry if it is self-invariant or unaltered in every way after being reflected by the plane. That means in this type of the symmetry, two parts become coincide after the reflection by the mirror. So now consider here, this is the one of that the triangle. Suppose if we consider it here, this is the mirror here. So now here we can see that this part of this triangle get reflected in this mirror, and which is exactly identical with this part here. That means we can see that the whole triangle similar to the original triangle, identical to the original triangle, and it is due to that the mirror reflection, and such a type of that the symmetric is known as the symmetry under the mirror reflection. Now we can observe such a type of that the mirror reflection type of that the symmetry in case of the cube also. Now here suppose this is the cube here. Now if in this cube here, so now in this diagram here, now if it get divided, now if we insert that the mirror, okay, along this direction, that means it get divided into the two equal parts. So this is the horizontal position of this the mirror. So we can see the reflection of this half part of that the cube inside that the mirror, and there we can see that the reflected and the original part, means you will get the original cube here, there is no change in its symmetry. Now if the position of the mirror is the vertical, that means exactly if we held the mirror vertically inside this cube here, so again you can see the half part of that the cube get reflected inside that the mirror, and both are identical. In case of that the third figure here, if we held the mirror diagonally, means like this here. If we held the mirror diagonally, means like this here. So again it get divided into the equal parts, and that half parts we can observe it inside that the mirror, and both are identical. Now then such a type of the symmetric operation is known as the mirror reflection type of that the symmetry. The fourth type of the symmetric operation is the inversion through a point or the center of that the symmetry. The center of the symmetry is also known as the center of the inversion. Now it is the point in the crystal such that if a line is drawn from any point on the crystal through this and extended to an equal distance beyond the point on the other side of the center, it meets an identical point. Now consider here, this is the circle. Now here this is O is now the center of the inversion. From the center of the inversion, if we draw the line on one of that, the lattice point on the side A, and say as that point is the A. So here that we can draw, if we connect it, then that is equal to the OA. If the OA is get produced in opposite direction, but through this point O, that is the center of that the inversion, then it meets to the point B. Therefore, here the OA is equal to OB. The points A and B are on the opposite quadrant. So here there is the symmetric operation, or there is the symmetry, and that is known as the center of that the symmetry. Now we can observe such a type of that the symmetry in this rectangular parallelopipe also. Suppose here this point O is at the center of this parallelopipe. Now consider here, this is the center of the inversion point. Now if we draw the line which meets to the point A on the one face of this one side of this parallelopipe, and if it get produced through this point O, then it will meet to the point B on the opposite face. Therefore here we can observe this OA is equal to that of OB. Similarly, we can observe it on the upper and the lower faces of this parallelopipe, that is OC is equal to the OD. Therefore, in both figures, the point A and B are on the opposite quadrants. Here the point A, in case of this parallelopipe, the point A and B are on the opposite faces, and when they connected, that the line joining these 2 points is passing through the point of this, passing through the center of that the inversion, that is the O, and therefore the point O is the center of that the symmetry, and such a type of that the operation is known as the inversion through a point or the center of that the symmetry. Now we are going to see the last type of that the symmetric operation is the space group type of that the symmetric operation, that is the screw type of that the symmetric operation. It is a compound type of the symmetry in which the translation and the rotation type of the operations applied successfully. That means we know that the screw having the spiral threads, when the screw, if we turn it inside the wall or inside that the wood, then what will happen there? Now like this here, then what will happen here? The threads of that the screw will go inside. If we rotate it into the clockwise direction, if we rotate it in the anti-clockwise direction, now then the screw moves in the upward direction. That means it moves away from that the wood or that the wall. Suppose here this is the screw. If we consider here the lattice point on that the threads here, then what will happen here? This is the one point here. When it get rotated, that times what will happen here? It will be get translated. That means here, in this process, in this operation, we can observe the 2 types of the operation, the 2 types of that the symmetry. One is the translation and second one is the rotation. So here from this point to this point there is the translation, and simultaneously through this rotation. So such a type of that is a screw axis is a line that is simultaneously the axis of the rotation and the line along which the translation of the body occurs. Thus, last one is that the glide plane type of that the symmetry. It is also the compound type of that the symmetry. A glide plane is a symmetric operation describing how a reflection in a plane followed by the translation. That means during this translation, during this type of that operation, we observe the two types of the symmetric operation. One is the reflection and second one is the translation. So now in this figure we can see that this is the glide plane. Suppose if we consider here, this is the one of that the lattice point, then what will happen here? Now it get reflected. Here is the reflection. Second operation is that it get translated. After that the translation, when it comes this lattice point, when it comes to here, again it get reflected. After that it will be get translated. That means here the lattice point within that the crystalline structure, it will move in a particular direction, in a specific direction through the reflection and simultaneously a translation. Now in this figure also, now we can say that this is the glide plane. Now this is the finger. When it get reflected at this position, at that times it get translated, and here this is the, now we can see here the position of that the finger like this here. After that, when it get reflected from this point, translated, so we observe that here, similar to that the lattice point. Now in this way, in case of that, if you want to move, or when the such a type of that the symmetric operation get operated inside that the crystalline structure, after that operation the structure will be remains unchanged, and such operations are known as the symmetric type of that the operations. Thank you.